At the end of this lecture, you should know what exactly feature maps are and how do they relate to convolutional layers. So far, we've only spoken of convolution, a kernel function sliding over an input matrix to produce a convolutional result. Now we'll speak of convolutional layers. Convolutional layers are generated using convolution, but it's not a single convolution result, but instead a convolutional layer is a collection of many convolutional result. These are feature maps. Consider an image. An image is basically a two-dimensional matrix where every cell in that matrix represents the value of a particular pixel within that image. For simplicity's sake, we'll just assume a grayscale image which has just one value to represent a pixel. This also applies to colored images or RGB images where we need three values to represent a pixel. Sliding a filter over this input matrix gives us a convolution result, also called a feature map. A feature map basically is a representation of certain features of the image. This is a good way to imagine it. A feature map is generated by using a particular kernel function on the input matrix. A feature map is comprised of a number of neurons where each neuron has received its value on the basis of the local receptive field defined by the kernel function that has been sliding over the input. Every neuron in a feature map has an associated local receptive field. Here you can see depicted on this screen the local receptive field of neuron I. This local receptive field, if this is an input layer, will be the pixels in the input matrix, or if it's one of the intermediate layers in the convolutional neural network, will be neurons from other feature maps. The number of neurons in this local receptive field is equal to the size of the kernel that we've chosen. Now, the size of the kernel is usually expressed in terms of width and height. A width of 3 and a height of 3 is a 3 by 3 kernel. Now, it's common practice to use small convolutional kernels as they have turned out to be more efficient while working with real problems. So, instead of a single 9 by 9 kernel, you might choose to stack two 3 by 3 kernels, and that is preferable. A smaller kernel size allows us to extract more information from the local receptive field. Neurons in the feature map get their values by applying the kernel function to the local receptive field, and adjacent neurons get their values when the kernel function slides over. And this is the stride that we spoke about earlier, the distance between successive receptive fields. This is a horizontal slide that you see depicted on screen, and this is the vertical stride. The neurons of a feature map all get their values by sliding the same kernel over the input matrix. So within a particular feature map, all the neurons have the same weights and biases because they've been generated using the same kernel. Zero padding may or may not have been needed based on what kind of convolution we are interested in. Now, feature maps are not a convolutional layer. Feature maps are a single convolutional result, the result of sliding a single kernel function over the input. Because feature maps are generated using the same kernel function, all neurons in a feature map have the same weights and biases. These feature maps have two big advantages over DNNs, which we've seen earlier: dramatically fewer parameters to train thanks to the local receptive field, where many neurons are connected to just a single neuron. These feature maps also allow the convolutional neural network to recognize patterns independent of location. The whole idea of using this local receptive field basically means a feature identified at a certain location is independent of its location. The same feature can be identified elsewhere in a CNN. We spoke of the kernel function as the filter earlier. The same term filter can also be used for parameters of all the neurons in a feature map collectively. These are called filter because the feature map highlights or filters specific patterns from the input pixels. And here is a graphical representation of a horizontal and a vertical filter. A horizontal filter will have positive numbers across the center of the kernel and negative numbers elsewhere. A vertical filter will have positive numbers across the center column of the kernel and negative numbers elsewhere. We've seen examples of this from the AI Shack website earlier. Once again, we've mentioned this earlier, but it's worth repeating. All neurons are not connected to all pixels. So, all neurons within a feature map are not connected to all pixels of the input. This is what makes CNNs sparse neural networks. So far, we've spoken about convolution. We know that convolution generates feature maps, but we haven't spoken about a convolutional layer. A convolutional layer consists of several feature maps of equal sizes. It's not just one feature map. A convolutional layer is much thicker because it detects many more patterns within a single image. When you stack several feature maps, each of which have been generated using a different kernel function, they together form a convolutional layer. This is worth noting as each feature map is generated using a different kernel function. Different feature maps have different parameters. A single feature map, the neurons within it have the same parameters, but different feature maps have different parameters and they basically highlight different patterns within the input image. These feature maps stacked together form one convolutional layer. CNNs can have two convolution layers one after the other. We now know that a convolution layer is made up of a number of feature maps, let's say 32 feature maps. That means each neuron in the second convolution layer, its receptive field will include the feature maps of all previous layers. So far, we've depicted the local receptive field as applying to a single matrix, but if you have multiple feature maps, then the local receptive field actually includes multiple matrices stacked one on top of another. It is this architecture of stacked feature maps and local receptive fields which allow our convolutional neural network to pick up aggregated, more complex features. The architecture of a convolutional neural network involves stacking up multiple convolutional layers such that the output of one layer feeds into another. These convolutional layers may be interspersed with pooling layers. These are subsampling layers which we haven't discussed yet. We'll look at that in the next lecture. Let's put all of these together. At the very left, you have a single feature map. The neurons in that feature map respond to a local receptive field. A feature map is generated using a particular kernel function. All the neurons within it have the same weights and biases. These feature maps come together. Many feature maps make a single convolutional layer. You put these convolutional layers, each of which have multiple feature maps together to get a convolutional neural network. There are pooling layers in between. Once again, just a little patience, we'll get to that. If you have a multi-channel image, for example, a color image will be made up of three channels, unlike a grayscale image which just has a single channel with a value for pixel intensity. A color image will have a pixel value represented by three numbers for RGB values. You can imagine an RGB image to be comprised of three layers. The local receptive field of a single neuron in a feature map will include all of these layers. Similarly, if you have multiple convolutional layers, which is how you'll typically build up your convolutional neural network, the local receptive field of a neuron in layer L will include the neurons in all the preceding layers. It will include the feature maps of all preceding layers. The output of a neuron in a convolutional layer basically depends on the corresponding neurons in all of the preceding layers, where corresponding refers to the local receptive field and all the feature maps which come within that local receptive field. When you apply a kernel function over an input matrix, what you get is a feature map. The weights and biases of a feature map is essentially the same because it is generated using the same kernel function. Feature maps serve to highlight specific patterns in the input image, such as horizontal lines, vertical lines, edges, and so on. They are generated using a kernel function which focus on these patterns. A number of feature maps put together make up a convolutional layer. A convolutional layer is typically deep, it has many feature maps.